Hey, hello everyone. Welcome to today's discussion of Educational Codeforces Round 186, rated for Div 2. We will be discussing problem A to E today. So let's start with the first problem. Problem name is New Year String. The problem says that we will call a string consisting of characters 0, 2, 5, and 6 a New Year string if at least one of the two conditions is met. The first condition is it contains the string 2026 as a contiguous substring, or it does not contain the string 2025 as a contiguous substring. Note that at least one of them must be satisfied. What does that mean? If 2026 is present, then it is, of course, a New Year's string. And if no 2026 is present, and no 2025 is present, then it is a New Year string. Okay, so here are some examples given to us. The string 2025, 2026, that is both are present. The first condition is satisfied, so it is a New Year string. In this, neither 2025 is present nor 2026 is present. So what does this say? The first condition is not satisfied while the second is satisfied. So this is a New Year string. In the third, 2 times 2026 are present. We needed only one presence of 2026. So it is a New Year string. And in fourth again, second condition is satisfied. That is 2025 is not present. Now, some strings that are not New Year. 2025 itself is present. So it is a case where the first condition is not satisfied and the second condition is not satisfied. So this is not a New Year string. In the second scenario as well, 2025 is present and 2026 is not present. In the third scenario, 2025 is present two times, 2026 is not present. Here as well, 2025 is present and 2026 is not present. It is 2022. Alright. So what does this we analyze? What do we analyze? We analyze that there should not be a scenario where 2026 is absent and 2025 is present. Alright. Now let's read the question further. So we are given a string s. We can perform any number of operations any number of times. Okay. Uh, Choose a character and replace it with 2025 or 2026. So what are the numbers given to us that are not let's say not a New Year's string? 2025 is present and some random numbers are present that do not contribute to 2026. Now maybe 2025 is present multiple times. Alright, but 2026 is not present. So what is the easiest way we can go from this string to a New Year string? If I can get a 2026, our first condition is satisfied and that is a New Year string. So what can we do? Just change 1 5 from 5 to 6. Alright, one operation. In one operation, we can for sure convert a non-New Year string to a New Year string. Okay, so what is the condition now? The problem is reduced to finding a non-New Year string. We are given a string. Find if it is a New Year string or a non-New Year string. If it is a New Year string, print 0 because no operation is required. If it is not a New Year string, then one operation is required. That is convert 2025 to 2026 by replacing 5 with 6. Alright, that is it. So let's move to the implementation part of this problem. So we were given a string. The first number is the size of the string and the second input is the string itself. Now iterate over every substring of size 4. Alright, why 4? Because 2025 and 2026 both correspond to a 4 length substring. Alright, now we got a substring of length 4. Now check if it is if it is 2026. Print 0 right away because it is a New Year string. Alright, and if 2025 is present, then in this case update our number of operations required to 1. Now if 2025 is present and 2026 is not present, we are sure that our string is a non-New Year's string. And if 2025 and 2026 are both not present, our answer is still 0. That is, this condition is never satisfied. So according to both the cases, we just print answer and we got this accepted. All right, let's move to the second problem now. The second problem reads as New Year cake. In this problem, Monocrab is going to buy a New Year cake. The cake must consist of at least one layer. The size of the top layer of cake must be 1. The size of the layer below it must be 2. And the layer below it must be 4, and so on. What does so on mean? The length of ith layer or size of ith layer is twice the length of or size of I minus 1th layer. Okay. So additionally, each layer must be covered with either white or dark chocolate. To cover layer of size k, monocrab will need k kilograms of chocolate. Each layer must be covered with exactly one type of chocolate, and these types must be alternate. If some layer is covered with dark chocolate, both the layer above, directly below it, and layer directly above it must be covered with white chocolate, and vice versa. Monocrab has A kilograms of white chocolate and B kilograms of dark chocolate. He wants to calculate the maximum number of layers that the cake can consist of, ensuring that he has enough chocolate for both of the types. Okay, so what does the problem say? In short, if we say monocrab wants a cake, and what does the cake look like? So the cake basically looks like this. Right. The first layer should be black or white, whatever we choose. The second must be white for sure because white is not visible. Let's analyze it with some other color. Let's say gray is fine. Gray represent white. Or let's say we color this completely with black. All right. So this one is black and this one is white. So if we choose the first layer, all right, that is our first layer is black. The next, all the layers are chosen automatically. And what are the size of the next layers? It is double the size of current layer. All right, this is it. So our cake can be either like this, that is black, white, or it can be reverse of. What do reverse mean? This is white. Okay. This one is white. This one is black. This one is white again, and this one is black again. So there are only two scenarios possible in this problem. And what does the problem statement say? We are given some quantity, let's say A quantity of white chocolate and B quantity of black chocolate. Okay. Now we have come to a conclusion that there are only two possible scenarios. Now for each scenario, how do we calculate the number of layers that we can form? Alright, let's say the first scenario was where we start with black. So one amount of black chocolate will be consumed. Alright, in second layer, two amount of white chocolate will be consumed. Now keep checking after each operation. Is the total count of or amount of white chocolate or black chocolate required after this operation, is it smaller than A or is it smaller than B, smaller than equal to? If it is, it is a valid choice. All right, we can take that layer. If it is not, then we have a constraint that we have finished off all our white chocolate or black chocolate, whatever currently we require. So in that scenario, we cannot go further to that particular layer. So the answer will be the layer at which we consumed all our required chocolate minus one. All right, because that is the number of layer we can form. And there are two possible scenarios: one for black, one for starting with black, and one for starting with white. Is it all right? So let's analyze some of the test cases we have. So this is the test case. In the first test case, we have 1 comma 1. Let's say black is top. And the second is case where we have white on top. So for black on top, how many layers can we form? In the first layer, we want one amount of chocolate. Do we have one amount of chocolate? Yes, we do have one amount of chocolate. So uh, one layer is possible. Now move to second layer. How many amount of white chocolate do we want? We want two size of or two amount of white chocolate. Do we have two amount of white chocolate? No, we don't have. So we stop right here. So what is the number of layers we can form with black on top? It is one. All right. Now similarly for white on top, for first layer, one amount of white will be required, and for a second layer, two amount of black will be required. Can we have two amount of black? No, we cannot have. So in this case as well, the number of layers that can be formed is 1. So our answer will be 1. Alright. Now let's move to second case where we have 1 and 2. Now for black on top. What is A and what is B? A is white and B is black. Alright. A is white and B is black. So we for black on top, on the first layer we will be requiring one amount of dark chocolate. So we have one amount of dark chocolate. So move forward. In the second layer we will be requiring two amount of white chocolate. No, we don't have two amount of white chocolate. So how many number of layers we can have? One. In white on top, we would require one amount of white chocolate for first layer. We have that, and two amount of black chocolate on layer 2. We have that. Now moving forward, we already have consumed one amount of white chocolate. Okay, one consumed. Now how many amount of white chocolate do we want? This is third layer. So four amount of white chocolate will be required. Do we have four extra? One is already consumed. Now number of white chocolates remaining is zero. So zero is smaller than four. So we cannot have the third layer. So answer will be two for white on top. That is our answer here. Similarly, you can go forward to analyzing these two test cases. So how do we have the answer? Just keep on iterating, that is multiply the current number by 2, that is the number of black chocolate or white chocolate we want in the next layer. And if that is smaller than equal to A, then our answer is possible. And what is the time complexity of this solution? What did we do actually? Let's see the implementation first. So what do we want? We want the first scenario in which the odd positions, that is first position, third position, and so on, will be acquired by A, and A is white. Okay, starting from white. So initially we have 1 as the number of chocolates required in current layer, and we keep on uh, adding I by 1, that is the layer number we will keep on increasing. And what is the amount of chocolate do we require? It is 2 to the power I minus 1. All right, because in the first layer we had one amount of chocolate, which is 2 to the power 0. In second we had 2, which is 2 to the power 1. All right, so number of layers minus 1 to the power 2 is the power of 2. That is the amount of chocolates we currently require. All right, and if we cannot satisfy this condition, that is uh, okay, if we can satisfy this condition, we can have this many number of layers and subtract that many amount of chocolate from A. Else, if we cannot satisfy, just break it, and that is the number of layers we can have. So that is it. Similarly, the same scenario for black on top. All right, when I is even, that is for second, fourth, and sixth, so on layers, we use white, while for odd layers for 1, 3, 5, and so on, we use black, and we just update the current layer by I, and at the end print the maximum number of layers we can have. That is it. Now let's analyze the time complexity of this solution. Okay, for each iteration I increases by 1. Okay, so how many iterations can I go to? Okay, in first iteration I is the amount of chocolate is 2. In second iteration the amount of chocolate is uh, okay, in first iteration amount of chocolate is 1. In second iteration it is 2. In third it is 4. And fourth it is 8, and so on. Okay, so in ith iteration it will be 2 to the power I minus 1. Okay, and this particular uh, iteration or looping will be stopped as soon as this number 2 to the power I is greater than either A or either B, min of A comma B, or let's say, let's for now assume it is greater than A. All right. In better scenario, we can assume it is max of A comma B, but it is very much same. So max of A comma B, what will that number be? That number will always be smaller than 1e6, that is 10 to the power 6. So what is the I for which 2 to the power I minus 1 will be greater than 10 to the power 6? Let's calculate. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. We are at this point at 10 to the power 3. All right. If we keep iterating, we are just taking log with uh, base 2. All right. We are taking because let's do some mathematics here. If we take log on both sides, it is as such. All right. And this I minus 1 is greater than log base 2, 10 to the power 6. So our order of running of our algorithm will be approximately log of n for each test case. Okay, and we are very much aware that log n works for very large amount of data up till 118. Alright, because for 118 log is around 60 or something. Alright, so t cross log of a, log of max of a comma b, log of 1 10 to the power 6. That will work for sure. All right, that is it. So this solution fits in our constraint. Let's move to the next problem for now. You can see that this solution passes as well. Okay, let's move to the next problem, which is production of snowmen. To create a fully festive atmosphere, Santa helpers have opened a factory for producing snowmen. Each snowman consists of three snowballs: a head, a torso, and legs. For the snowball to be stable, the ball forming the legs must be strictly larger than ball forming the torso. In turn, the ball forming the torso must be strictly larger than the ball forming the head. Formally, if we denote the size of head, torso, and legs by ABC respectively, the snowball will be stable if and only if A is smaller than B is smaller than C. That is, the head is smaller than torso and the torso is smaller than legs. At the snowman production factory, there are three conveyor belts, each consisting of n snowballs. The first conveyor belt consists balls of size A1 up till AN. Second consists balls of size B1 up till BN. And third consists balls of size C1 up till Cn. The conveyors are cyclic. In other words, after the elements numbered n, the element number 1 follows again. And we can consider that ball numbered I and ball numbered I plus n are on the same ball. It just means that balls are cyclic. That is, conveyor belt keeps on revolving and the neighbors keep on coming one after another. After nth element, first element will appear. This is what it means. To produce snowmen, it is necessary to specify three parameters I, J, K, indicating which balls on each conveyor the production starts from. After that, the snowman will be assembled from the balls as shown. The first snowman will have a head of size AI, torso of size BJ, and legs of size CK. Second will have AI plus 1, BJ plus 1, CK plus 1. What does this mean? Okay, let's visualize what it means. So these are some snowballs. All right. Black just means that these are for head. These are cyclic. Now here there are some snowball which are for torso. Then if we choose some AI, okay, some I and some J, then uh, these two will be clubbed. These two yellow ones will be clubbed. These two will be clubbed. These two will be clubbed in cyclic order. All right. And then again, these two will be clubbed. All right. This is happening in cyclic order. This is what this particular line means. The parameters I, J, K must be chosen in such a way that all n snowmans are stable. Your task is to count the number of suitable combinations of parameters. Okay, so we have three such conveyor belt. There is a conveyor belt here as well, where n snowballs are present. Now we need to choose some I, some J, and some K such that the snowballs formed due to that particular combinations are all stable. That is, all the snowballs formed uh, using that particular iteration ijk. They are all stable. All right. So what does this mean? Okay. So this mean that if we first try to combine torso with legs. All right. Let's say this particular torso is stable when we combine with this particular head. That is, all these are stable. That is, if we choose J as this and K as this, then all the combinations that are formed, this with this with this, and so on in cyclic order, they are all stable. That is, C of K. How can we write this mathematically? If C of K is greater than B of K, C of K plus 1 is greater than B of K plus 1, and so on. Then this particular okay, B of J. Then this particular combination J comma K is possible. Now let's say with this particular J, there are X Ks that gives a correct or stable order. Okay, what does stable order mean? That it means that all the snowballs formed using these two as starting points, they are stable. If there are X Ks which give stable snowballs, all stable snowballs, that is all n snowballs, all stable snowballs. Then uh, for a combination I comma j, how many possible uh, tuples are there? That is, how many possible ijk are there? Because I comma j gives stable, then j gives stable with k. All right. Then there are total X possible scenarios where we get stable combination of snowballs. All right. So what will our final answer be? So for this J, how many stable indices are there in C array? Okay. What do I mean? If we want answer, we would rather reduce our problem statement into this statement. For each J, find how many K leads to stable array. Alright. Now for every pair I comma j, the answer is okay. This, let's say this is x. Then answer is x, and we can see that the value of n is 5000. So n square is very much computable. All right. So for every pair, we can find uh, the answer if we already have calculated answer for each j. But how can we do this? If we start from every j, Our aim is to find how many k uh, leads to stable snowballs for a given j. Okay, if we iterate over all j and all k, and then there are n snowballs, and we check that if this particular order gives us the stable snowballs, then it will be O of n cube solution. All right, which is not optimized to pass under this constraint. So we need to optimize this a little bit. All right. So how can we do it? Do this. Let's say this particular pair. Let's have a test case for understanding this. Let's say this is the test case. For this J, okay, let's copy whole test case. Let's say for this J, how many options are there for a possible K? This is an option, this is an option, this is an option, this is an option, this is an option. Every possible index is an option for each J. So how many possible combinations are there for uh, J and K? There are total n into n combinations. All right, we can choose 1 comma 2, 1 comma 3, 3 comma 1, 2 comma 1, anything for J and K. But there are scenarios where some pairs are not stable. How to find them? Okay, in each pair there is some bx greater than the corresponding c. Let's say the corresponding y for this particular pair that we have chosen. And what remains constant if we have chosen this as our j and this as our k, then for all the upcoming choices of pairs, the difference between j and k will remain constant. Here, the difference between j and k was 2. So for the next pair formed, the difference will be 2. Next pair, the difference will be 2. Alright, its index is 2 and its index is 4. So 4 minus 2, it is 2. Alright, this will remain constant. So for in each pair that is not possible, in each unstable pair, there is some bx greater than cy. So, and the word some means that there can be more than one. So how do we define some unstable pairs? That is, this particular unstable pair will uh, remove these possible scenarios from our choices of pairs. How can we do so? Let's see. Okay, we already observed. What was one of our observation? That for a possible choice of j comma k, the difference remains of indices for each pair remains constant. Alright, so if these two, what is some possible index that gives unstable uh, pair? This and this gives us unstable pair. Okay, so this will be part of every j and k which have difference 1. Alright, what does this mean? Because index 1 and 2, okay, zero based indexing 0 and 1 gives a unstable pair. So every jk which has difference 1 will be unstable. All right. This is a very powerful observation. Let's say we started with J as here and K as here. So what will be the next pair? This and this. And what will be the next pair? This and this. And we know that this pair is already unstable. Okay. So for each unstable pair, if we find another unstable pair of same difference of indices, then no need of subtracting anything more. All right, because all the possible pairs that were unstable due to this difference has already been removed. Okay, so what did we observe? We observed that for removal of pairs, iterate over all the possible differences and all the possible differences and all numbers corresponding to that difference, or all indices, or all pair of indices corresponding to that difference. All right. Now, if this particular pair is unstable, just remove all the corresponding unstable j comma k. All right, from our point of consideration. After this removal, we will be left over with all the possible j's and k's that are stable in itself. Now do the same operation for I and j. How many pair of I and j are unstable? Remove them. So we got, let's say, stable ij pairs and stable jk pairs. All right, using this particular operation, we removed all the pairs that were unstable from all possible pairs. That is, there were n square possible pairs, and we removed all the unstable from it. So how many are left? What is the criteria for left one? They are all stable. So for each choice of I, we have, let's say, n1 number of stable j's, and for each choice of j, we have n2 number of stable k's. All right. So due to this, and how many choice of I are there? So okay, there are n choice of I, and let's say there are uh, n1 stable I comma j pairs. All right. So we multiply n1 into n. That is, these all three conditions are uh, independent. So according to permutations and combinations, we have three options. So they will be multiplied because they are all the three are independent. Here we have AND operation as our requirement. Okay, we have to choose one I, then one j, and then one k. So how many choices of j are there? N1 choice of j, and n2 choice of k, and n choice of I. So this will finally give us the final answer. All right. So let's move to the implementation for now. Then we will be analyzing the time complexity for this scenario. Take input of A, B, and C. Then what did we discuss? We discussed that we will iterate over the differences. Start from difference 0 up till difference n minus 1. This is the possible, all the possible scenario. All right, because minimum index is 0, maximum index is n minus 1. So the difference is n minus 1 overall. Now iterate over all the possible starting positions. Okay, so for this position, if we find a unstable pair, then a count of choice for j will be reduced. All right. Similarly, for pair K, we found an unstable pair between A and B. Okay, this was for pair K and this was for pair J. So we found an unstable pair. So reduce counter by 1. Total number of cases were n. Total number of choices for J were n. Alright. Now at the end, just output n into the choices for J and choices for K. That is it. Okay, so this is as we discussed. So for each choice of J and K, where we are having n options. Alright, and each at each difference is if we found a unstable pair, one choice for J for every I will be reduced. Alright. Why? Because for this I, if the difference is 2, what is the choice of J? This is the choice of J, and we found that later on with this difference we found an unstable pair. So this possible pair will not be possible, will not be correct. All right. Similarly, this possible pair will also not be correct because this is not correct. Difference is 3. This is also having difference 3. So this is also not correct. So reduce 1 from the choices of uh, K we have for each J. All right, that is it. So what is the overall time complexity? We iterated over all the differences and iterated over all the differences and all the indices. So there are n O of n differences and O of n indices. So overall time complexity is O of n into n. Similarly for this part, which is again O of n into n. So O of n into n plus n into n is O of n into n. That is it. And we see that O of n into n is pretty much computable in this scenario. Now let's move forward to the D problem of today, which is Christmas tree decoration. Okay, so let's move to the next problem, which is Christmas tree decoration. A group of n people decided to decorate the Christmas tree. They have n plus 1 boxes of decoration numbered from 0 to n. Initially, the ith box contains AI decorations. We say that a permutation P of size n is fair if it is possible to hang all the decorations on the tree using the following process. Person P1 takes decoration either from box 0 or from box P1 and hangs it on the tree. Similarly for P2, it can take from 0 or box P2 and so on. After person Pn, person P1 follows and the process repeats until all the decorations are on the same tree. During this process, there should never be a situation where person I needs to hang a decoration, but both box 0 and box I are empty. If such a situation cannot be avoided, the permutation is not fair. However, if the people can choose from which box to take a decoration during each step in such a way that situation does not arise, then permutation is fair. This last line or last paragraph basically means that we have independence of choice of the box from which that particular person will choose. That is, we will direct that person that you choose from P1 or you choose from P0 and so. Okay, what does the overall problem statement mean? There are some person, let's say P1, P2 up till Pn. We arranged them in some order. Let's say P2 is first, then P3 is there, or P5 is there, then Pn is there, and at the end P1 is present. All right. Now P0 is always at the beginning. Now a game will go on in this way. That is, P2 will pick up one decoration, P5 will pick up one decoration, Pn will pick up one decoration, P1 will pick up one decoration. In the second step, P2 will pick up one decoration, let's say P5 has finished the number of decoration. It had only one decoration with itself. So it will go on to P0. Hey, give me one decoration. So P10 said, okay, take away one decoration. Now Pn had decoration with it. So it uses its own decoration. Similarly, this goes on and P1 again has its own decoration. All right. Now P2 has its own decoration and P5 does not have a decoration. All right. And P0 also do not have a decoration. Now what happens? There are some scenarios for us. Okay. Okay. So here it is. The problem statement says that our permutation is fair if and only if it is possible to hang all the decorations. That is decoration for uh, P0, P1, P2, every one of it has been utilized. So here we come to a point where P5 does not have a decoration and P0 also does not have a decoration. So every one from Pn to P1 should also not have a decoration. Then only this particular permutation will be fair. All right. Now let's analyze the scenarios for a fair permutation. Okay. So if we analyze it clearly, we used two decorations for everyone from P5 to P1 and three decoration only for P2. All right. If P5 had an option, then three decorations would have been chosen for P5, and if Pn was the first index where choice was not possible, then from Pn up till P1, all would have total two decorations utilized. Now, what are the possible observations of constraint we have? The final choice of number of decorations for each I must be greater than equal to AI. Alright. And second observation, there will be few numbers of, okay, the possible number of decorations for every particular person will be x comma x minus 1. What does this mean? That is, it means that if the starting pair chooses three decorations, then the ending pairs will have to choose two decorations. At least, uh, not at least, exactly two pairs. Why so? Because let's say P1 chose one decoration. So is it possible to have such a iteration? This iteration is complete. This iteration stops here. All right, because this has P1 has chosen already one decoration, so it cannot choose in second iteration. Now in third iteration P2 chooses, but the third iteration cannot start before P1 has chosen. All right, because they are going in order. So this gives us the conclusion that only choice can be only of form x comma x minus 1. So this gives us the scenario where a decoration is not possible for a permutation. let's say the highest number is 3, or let's say it is 4. So every other number, let's say we have 2, we have 1, we have 3, then 1 and 2. Then P0 must be sufficient that all these number gets the choice to pick up at least 3 decorations. So observation, every number should have option to be equal to max minus 1 at least. Okay, so this is max, that is 4. The person with 4 amount of decorations can have only 4 or greater than equal to 4 number of decorations chosen at the end, because that is the very first conclusion. Okay, so due to second conclusion, we come to a final conclusion observation that all numbers apart from 4 should have value at least 3. So what is the number of decorations P0 should have so that these all have at least 3 decorations? It is equal to 3 minus 2 plus 3 minus 1 plus 3 minus 3. All of them have to reach 3. Okay, so how many number of decorations are required? This is what we are calculating. This is the amount of decorations P0 should have, because this person we have two choice of decorations from its own box. Now after its own box has finished, it will look upon to P0 for one extra decoration. So if, let's say this number is X, if P0 is smaller than X, answer is okay, no permutation is possible. Alright, now this is one of the case for our final solution. Let's analyze another case now. Case 2. What can be another scenario? Another scenario can be for all the numbers reach up till 4. Okay, in this scenario, everyone is independent. That is, every particular permutation is possible. How? If every one can reach up till 4, then whatever permutation you have. Here we had 4 2 1. Okay, 4 2 1 3 1 2. 4 2 1 3 1 2. All right, 4 2 1 3 1 2. We were sure we are sure that we can reach up till this particular scenario, or even and P0 is greater than equal to 0, and we can still have some P0s, that is we can have some 5 4 or something like that. Every number above greater than equal to 4, when a number is, all the numbers are equal to 4, every number that reaches above the value of 4 will take the decoration from P0 only. Okay, and everyone has the free will to take from P0 the number with minimum number of decorations. The index with minimum number of decorations can also take from P0, and the person with highest number of decorations, 4, he can also take from 0. There is no restriction. Okay, so any possible permutation will be possible. Why? Because everyone can reach to 4. Now uh, the ones that have value greater than equal to 4. All the values greater than equal to 4 are chosen from P0, and P0 is not racial. He gives value to everybody, irrespective of what initial value he has. So everyone can reach to 5. If he can reach to 5, 1 can reach to 5, 4 can also reach to 5, and vice versa. So every particular permutation is possible. Alright, this is what this observation, that is case 2, says. Let's highlight all the cases we have so far. Let's write it down. If all can reach up to maximum element, then any possible permutation will be possible. Now case 3. What is the case 3? We have analyzed the case where some cannot reach up till 3, and we have analyzed the case where all can reach up till 4. So the leftover cases, some of them can reach to 4, and some cannot reach to 3. Reach to 4. So they can reach to 3. This is a possible permutation, okay? So because x and x minus 1 is a very much possible case. We have total 6 elements. Okay, so we are sure that final choice of decorations will look like this. Now we have a constraint that final choice of each person should be greater than equal to AI. Now there are some 4, and initially we have persons as 4, 2, 1, 3, 1, 2. Now this 4 can never go to this part because of this very condition. Alright, this very condition. So this particular 4 must be present in this part. Alright, so what is our final answer in this case? We choose a position, because let's analyze this as some empty sequence we have. We have 6 empty sequence, and 4 can go to these 3. Alright, so choose one from these 3. What is the way to choose one from this 3? 3C1. And for the rest, that is 1, 3, 1, 2, and 2. 2, 1, 3, 1, 2. They can go, let's say this was the index chosen for 4. So they can go here, or here, or here, or here. They have very sorted scenario. Okay. All the leftover dashes will be assigned to them. Now, for the very first choice, for the 4s that we had, arrange them among themselves. Factorial of count of 4 multiplied by factorial of leftovers, that is 1, 3, 1, 2, and 2. They both will be they all will be arranged among themselves. And even if 1 comes here, we know that we have P0 in excess amount, that we can do 3 iterations on any possible permutation, and then also one will be left over with us, such that this particular value translates to 4. Alright. If you do not understand this part, listen this again. What did I say? Whatever permutation we have after assigning 3 decorations, irrespective of value or person, on index 3, it will have one choice of decoration. Simply because P0 is not racial. Okay. Now, for this part, arrange them in any order. So, arranging them is equivalent to taking factorial. So, n minus count of 4. All right. So, these are the possible scenarios that we have: P0, P1, and P2. Let's move to the implementation part. Okay, so first implement case 0, where P0 is smaller than X. What is X? Maximum element minus 1 minus each of the elements that are not maximum. So, iterate from 1 to n. First, we sorted our vector. Why? We want the maximum element. So, sort it so that maximum element comes to the right. We won't be applying operations on all the maximum elements. If there are multiple 4s, we want this operation to be applied only with values smaller than equal to 3. All right. So we will stop at point where we get 4. So start from 1. At the point we get a value equal to the largest value, that is 4 in this particular scenario. Our count of maximum element is equal to n minus I plus 1, that is leftover elements, and the value of x will be added upon by the maximum value minus 1 minus the current value. That is 4 was the maximum value, 3 minus current value. Now, for the first case, if the required amount is greater than the available amount, okay, P0 is smaller than X, same thing, then uh, how many number of permutations can we have? No permutations. So print 0 and return simply. Now the second scenario, where after applying operations such that all of the values translates up till the maximum value. In this scenario, answer is factorial of n, because all permutations are possible. So how can we translate every element to n? We wanted to translate, how can we translate every element to maximum element, value of maximum element? Initially, we translated every one to one lesser than maximum element. That is, maximum was 4, we translated it to 3. So how many number did we translate? It is equal to n minus the number of maximum elements is the number of elements translated. All right. And for those elements, one value will be required. All of them were translated to 3. Now we want to translate them to 4. So 1 for each. How many numbers are there? N minus ma. And how many operations were required or decorations were required to translate up till 3? That is cur. So if cur plus ma is smaller than v0, that is this particular scenario, then all conditions are true. Output factorial of n. You can make your own templates as well for calculating factorial and NCR. I will be providing my code. If you find it good, then you can copy paste my particular template as well. Now the third scenario, which is the left part. So we want to find how many elements will be translated to 4 and how many elements will be translated to 3. Okay. So how many elements will be translated? The number of elements that are already 4, they will be there for sure, and the number of elements to which P0 can translate to 4. Subtract the number of decorations required to translate up till 3, the number of decorations left over now with P0. Those are the number of elements that will be distributed to all the 3s so that they translate to 4. Alright. So V0 minus cur. Now, what was our answer? NCR. Where what was N? N was the number of force and R was number of force already present in our array. So how many force are already present? ME force are already present, which we calculated here. And MX is what we calculated here. Now, two factorials. First was count of 4, which is equal to factorial of MA, and n minus count of 4, which was n minus MA. That is it. And take modulos and just print the final answer. So what is the overall complexity? We had a loop of n for calculating uh, the maximum element and required amount x. We had a sorting function, which is n log n. And later on, these are just O of log n operations. Why log n? Because calculating NCR is uh, equivalent to calculating binary exponentiation. Okay, if you do not have knowledge about it, you can just read it on CP algorithms or just black box black box this particular template for yourself. All right, so that is it for problem D. Let's move to the problem E now. Okay, so let's move forward with discussion of problem E. Monocrap has n friends and decided to give a New Year gift to each of them. He has also prepared n boxes to place the gifts in. The beauty of ith box is AI. Every box contains at most one gift. Monocrap wants to gift worth at least yi coins to ith friend. Alright, here it means that at least yi coins will be given. Apart from that, other conditions can be there. Additionally, he knows that ith friend will be happy if at least one of the following conditions hold. The gift is in a box with beauty at least xi. The gift is worth at least zi. Okay, so there are two conditions for a friend to be happy. The first condition is that he has yi coins at least. All right, he will be given yi coins later on if he receives a gift worth zi, where zi is greater than yi. So he requires extra zi minus yi coins to be happy, or he requires a gift with beauty at least xi. Your task is to help Monocrap calculate the maximum possible number of friends he can make happy if he has k coins. Alright, so this is it for the problem statement. From the problem statement as well itself, we can have some conclusions. Every friend must be given yi coins. So for a friend to be happy, there are two conditions. Gift a gift of beauty, gift of beauty greater than equal to xi. Second condition, coin, use coin, zi minus yi. Alright, this is the conclusion from problem statement, overall conclusion from the problem statement. So what do we, what are the choices do we have if we try to approach this problem greedily? Because that's what the constraint forces us to do. N is 2e5 and k is very large. So for approaching greedily, we will have two choices. First, uh, utilize two choices. Choice one. approaching it greedily. All the vague implementations or ideas that we have, just write it down. One of the vague idea could be choice one, maximize the friends, happy friends, using coins. Then maximize the leftover with beauty. Second, do the vice versa. What do vice versa mean? First, maximize with beauty, then maximize with coin. Okay, this is the choice with us. So let's, because we have two vague ideas, let's analyze both of them. What if we use coins to maximize the number of friends first? Okay, let's say a friend has, a friend wants beauty 5 and coin 2. Another friend, okay, small values of beauty and coins both. Another friend want 5 coin and 5 beauty. Currently, we have 3 coins and 3 beauty. Only one gift with beauty 3 and coin 3. So for maximizing the happy friends using coins, what we will try? This friend require 3 coin, so just make him happy using 3 coins. So this friend is no more with. Okay, he is with us, but he is happy now. Now we are left over with one more friend. Here we had beauty. All right. Now can we make him happy? No, because he want beauty 5 and coin he want. Okay, we have 3 coins. All right. Here, this was the scenario. Really sorry. This was the scenario. He wants, 3 coin, 2 coin, comma 2 beauty, or 5 coin, comma, okay, 5 beauty, comma 3 coin. Now how many coins we have? We have 3 coins and we have 3 beauty. We first maximize the friends using coins. So greedily, if we want to maximize the happy uh, friends, then what we will do? Find the friend who wants minimum number of coins. Then use uh, those number of coins and go on with uh, the leftover friends who want the minimum number of coins. So this is the friend with minimum number of coin. Make him happy. Now we have one coin left over with us. Now can we make this friend happy? We have one coin, so we cannot make him happy. We have 3 beauty, so we cannot we make him happy. But so this particular idea will give us the answer 1. But is it true? We could have used this beauty to make the first friend happy. Now we could have used over this coin to make the second friend happy. So we have a edge case with us. So this vague idea we had is wrong for sure. Alright. The second vague idea we had, maximize the friends, happy friends. With beauty, then maximize the leftover. Didn't we do very much the same thing in this part? Yes, we did. So vaguely, it appears that this idea is correct. Now let's move to analyzing it further. Okay, so let's say we had uh, we had a construction where we can use all the m, okay, possible construction where we use all the m beauty box. Can a construction with m minus 1 boxes give us better result? Let's analyze. Let's say uh, we do not use all the boxes to uh, make our friends happy. We use m minus 1 boxes. Okay, so one of the boxes is left over and it requires coins to be made happy. Okay, because total was x plus y. X were made happy. Uh, X were made happy using beauty and Y were made happy using uh, coins. All right. Now we say that we saves one of them. All right. Uh, to be utilized using beauty or to be made happy using beauty. So x minus 1 are there that can be made happy using beauty now. Now how many can be made happy using coins? Let's say after making all the y persons happy or y friends happy, we are left over with 3 coin and the beauty which we removed just now uh, was such a friend which required 4 beauty to be made happy and 3 coin to be made happy. In this case, we can make one person more happy. Okay, using coins. Can we make one person more happy using beauty? No, we already had the very optimal condition. If we do not make this person happy using beauty, we can never make another person. We had such a optimized version of our uh, choice of beauty for boxes. Now, overall, how many numbers of people can be made happy? There are x plus 1, x plus y number of peoples that could be made happy. Or another scenario where he could be made happy using beauty 4 and coin 4. Now, coin 4 is greater than coin 3, the number of coins which we uh, are left over with. So in this scenario, this 1 will not be added and overall answer would be x plus y minus 1. So we come to a conclusion that choosing construction with m happy friends due to beauty is best. Alright, keeping in mind that we already had the most optimal version of choice. So let's try to have a construction of choosing those M happy friends. All right, we are not sure that we can make all the M friends happy, but we want to maximize the value of M. That is what our initial assumption was. All right, so let's have a example.
how can we find the best possible construction where we choose maximum number of friends who are happy due to beauty? Okay, if a beauty is 4 and another beauty is 7 and a friend requires 3 beauty, what is best to make this friend happy? Of course we won't use 7 here. By Because we have a choice where we use this 4 and we make this friend happy. Maybe later on some friend come who requires 6 amount of beauty to be happy, so we can utilize this 7 to make this 6 happy, but we cannot utilize this 4 to make this 6 happy. So we will want to have wasted our minimum number of beauty at every step. All right, so how can we do this? Sort on the basis of, sort both the arrays, sort beauty array and all the friends on the basis of the beauty they require to be happy. All right, now it is sure that this 4 will make one of them happy. Let's say there were 3 friends, one friend with requirement of beauty 2, one friend with requirement of beauty 3, another friend with requirement of beauty 3. Now this friend requires uh, 8 coins to be happy, this friend requires 2 coins to be happy, this friend requires uh, 1 coin to be happy. All right, what is the best choice? If we pick up this friend, later on we are left over with a friend who requires 8 coin to be happy. We won't want that at the end uh, we would be wasting our coin. All right, we want to save our coins as well, so it is best that we choose the friend with maximum coin requirement. All right, so that the leftovers could be uh, made happy using coins later on. Okay, so now for each beauty each beauty box, find the friend who can find the friends who can be made happy using that box. Among those friends, choose the one with maximum coin requirement. All right, now continue this process, remove that friend and continue this process uh, later on. Keep continuing this process for all the possible boxes that we have. At the end we are left over with some friends that need to be okay. Why is this optimal? As we discussed here, that is, this construction should be optimal. Why is this optimal? Because of this very scenario. 4 was used to uh, make a person happy that could have been made happy by 7, but 4 is not used to make a person uh, 7 is not used to make a person happy that could be made happy using 4. Okay, this is the reason this choice of beauty is optimal. Also the choice of leftover elements who are meant to be make happy using coins, that is also optimal, because at each step we have chosen a friend who requires maximum amount of coins to be made happy, so the leftovers are minimum ones. Okay, so now satisfy the left maximum number of friends using coins. This is very much greedy. Why? Because let's say a friend who wants 5 coins to be satisfied. He can be satisfied using 2 coins as well. Okay, so sort it in the order of increasing order of coins and keep iterating unless and until you find an element which cannot be made happy. Later on, up till the element which could be made happy, add it to our answer. And the ones who could be made happy using beauty, they are already in our answer. So the sum of these both is our final answer. So let's analyze few things. Let's say we have a construction of all the people we have chosen. If we remove an element and try to insert some other element, uh, is it optimal? Because we already have the optimal choice of beauty. It is not optimal due to choice of beauty. Now, uh, we are also having optimal choice of coins. So if we remove it, now more number of coins will be required for another construction. All right. So that is why this construction gives us the correct answer. So let's move to the implementation part. Whatever we discussed, we are just implementing it right here. We have NMK. N represents the number of friends we have. M represents the number of beauty gifts we have. And K represents the number of coin. Take input the number of beauty gifts, sort them as we discussed due to greedy approach. Now take input the details of friends. 0 represent the number of beauty required to make him happy. 1 represent the number of yi, that is number of coins that need to be wasted in any scenario. And uh, third input represent the number of coins required to make him happy using coins itself. Now what did we want? We wanted first the amount sorted in the form of beauty, then in the form of coins. All right. And not coins required to make him happy, total coins required to make him happy, the extra coins required to make him happy. This need to be wasted anyhow, and this is the extra coins required. Okay. Now, because we already waste these many coins, k subtract this value from k, that is total coins we have. Now sort it as we discussed due to our greedy approach. Now we at each step of choice of some elements that could be satisfied using current beauty, we want the element with maximum coins to be removed. Okay, maximum coins required to make him happy, that element should be removed at every scenario. All right. So for first gift, iterate over, because this is in ascending order. We sorted the temp has first value as the number of beauty required to make him happy. So the smallest friend with smallest amount of beauty required comes first, and all the friends that can be satisfied using the first gift, we have them uh, using this loop and insert their number of coins required using a priority queue. Why priority queue? We want to remove the person with maximum coins required. So insert the number of coins required for current person. We have a group of all the peoples that can be satisfied using this current gift, and among that we just pop out the element who required, or the person who required the maximum coin. All right. And because we satisfy this person using beauty, just add 1 to our answer. Now the leftover elements who could have been satisfied using coins, just insert them. Now we want to maximize the number of people who are made satisfied or happy using coins. So sort them first of all, because we already have a priority queue, so it has all the elements sorted in decreasing order. Insert in new remaining vector. Remaining represents the remaining number of people and how many coins they require to make themselves happy. Because it is sorted in reverse order, just reverse it to sort it in increasing order. Now iterate over to all the elements at the point the number of coins required could not satisfy this person. just break. And if coins can be used to satisfy this person, satisfy him, and increment the number of satisfied people. At the end, just print the total number of satisfied people. That is it. That was the discussion for today. Thank you for joining, everybody. Have a great contest ahead. You can try F1 as well. F1 is quite doable if you have enough motivation, because uh, people were already tired of solving up till E. So they did not solve F1 today. But it's really solvable. I will myself try it after now. Thank you for joining. Have a happy contest ahead.